Welcome to VLSI circuit design course. The VLSI meaning, the full meaning of VLSI is very large scale integration. Very large scale integration. So here the unnecessary information, you already know it. Okay, what is the purpose of this course? We will be trying to know how ICs are made, how ICs are designed. So here, why ICs are necessary? Because all the thing that we are using today, that is made of ICs. Okay, like processors, CPU, DSP. DSP means digital signal processor. Controllers, that like your microcontrollers. Memory chip, RAM, ROM, EEPROM. Analog, mobile communication, audio, video processing chip. Programmable, PLA, FPGA. All those ICs. Embedded system used in cars, factories. Network cards, system on chip, SoC. So these are all made of ICs, and these are all the name of our example of ICs. Okay, if these are not present at this country, that means we are actually at 1946. Okay, after 1946, a revolution has happened. The world has never seen a huge growth in technology without the help of IC. If there was no IC, it could not be possible to see these amount of technological advancement. Okay. Now VLSI, the meaning of VLSI is very large scale integration. Integration means integrated circuit. That means you are going to integrate multiple devices on one substrate. One substrate means one body, that means one package. In one package, you are going to integrate multiple devices. Devices means diode, transistors, all those things. You are going to put a lot of diodes and transistors in one substrate. Substrate means body, one package. So that is called integration, and the whole thing is called integrated circuit, that means IC. Now here, one very interesting thing, why the course is called very large scale? What do you mean by very large? How large is very large? The question is here, how large is very large? Now, this information is not valid. This information is not updated because this information changes after 6 months. Okay. So here I just put this information to give you an idea. To give you an idea, not the actual value. These are all previous values. So you can actually ignore these, but just get an idea. First level is called SSI, that means it's small scale integration. When your transistor number, the number of transistors in your IC is less than 10, you can call it SSI. MSI, medium scale integration. That means when your transistor size, transistor number is more than 10 but less than 1000. Here, can you see an exclamatory sign? That means this sign means this number is not actually correct. This one is for illustration, to make you understand only the things. MSI, medium scale integration. Then you have LSI, large scale integration, when the number is more than 1000 but less than 1 lakh. VLSI, very large scale integration, when the number is more than 1 lakh and less than 1 crore. 1 crore means maybe 100 million. Then comes ULSI, that means ultra large scale integration, or SLSI, super large scale integration. This one, when your transistor number is more than 1 lakh, no, 1 crore, that time you can call it SLSI. Like your CPU, like Core i3, Core i9, Core i5, Ryzen 5, Apple A11 Bionic, A13 Bionic, all those chips, Snapdragon 865, all those chips are under SLSI. Now, the first computer was made in 1832. This is not an electronic computer. This is not even an electrical computer. This is a mechanical computer. This is called the Babbage difference engine. Who made this? Charles Babbage. He is the inventor of computer. Okay? He created these in 1832. 18, not 19. That time it had it had 25,000 moving parts, and it cost 17,470 pounds that time, not this time, that time. Okay, so what it does actually, it actually does the difference between two numbers. That means it can subtract two numbers and show you the result. How? You can see there are some gears, right? Some gears and some numbers are there. 3, 1, 1, 1, 1, 1, 3, right? And there you can see now some numbers 0, 2, 5, 1, 1, 1. And at the middle you can see some numbers 0, 0, 0, 3, 1, 0, right? Something like that. So these numbers are moving because the gears are moving. This is similar like the lock you can see inside a briefcase or a suitcase. Combination lock, right? You have seen something like that, combination lock. Hello? Are you understanding?
Yes, sir.
Okay.
Yes, sir.
You can see these sort of things inside a briefcase or suitcase, combinational lock. The combinational lock happens when you rotate the numbers, right? What you do here, you rotate the numbers, the gear will rotate, and automatically the gear will change the middle row. The middle row is the answer. The left row is maybe A, the right row is maybe B, the middle one is the answer. So if you change these and set a number, the middle number will be automatically changed, and this will be your result. Understand? Okay. Now this is called first computer because these actually triggered human to think about making an electronic computer later on. This one was first electronic computer. This is from 1940 or 1946 actually. 1946. This is from 1946. This is made of vacuum tube. What is vacuum tube? You can go to YouTube and search what is vacuum tube. You can actually get an idea about that. Vacuum tube is a mechanical, or what should I say, physical tube that can be represented, that can be used to represent ones or zeros. Okay, so this is completely a vacuum tube computer. Now the vacuum tube can only contain one bit. One tube will contain one bit. So remember, so if you have to make a big computer that has, let's say, 1 megabit, not megabyte, megabit, 1 megabit, that means 1 million bit. That time you will be needing 1 million vacuum tube. Remember, 1 megabit is not a big deal right now, nowadays. It's very small. But that time, 1 megabit was very, very, very big. So think about this. For 1 megabit, you need to use 1 million vacuum tube. This is all vacuum tube computer. That's why the size of the computer is very big. The size of the room is very big. This is one computer. And 1, 2, 3, 4. 4 operators are there. So 4 of them are operating the computer. Understand? This was ENIAC, E-N-I-A-C, ENIAC, the first computer, electronic computer actually. After 1 year, the transistor was created. Okay, let's skip some pages and go to the transistor. Okay. After 1 year, the transistor was created. See, the first transistor, this is from Bell Lab, B-E-L-L, Bell Lab. Bell Lab is a lab of AT&T. AT&T is a big telecommunication company in the world. It is based in what? Based in where? Based in USA. This is based in USA. So Bell Lab is a very big telecommunication based lab of AT&T company. There, 3 scientists invented a transistor. That is the first transistor. That is in 1947. Remember, 1947. That was a very big milestone for us. These are the three scientists who created or who invented the transistor. Left side, John Bardeen, right side, Walter Brattain, at the middle, who is the main guy, William Shockley. That's why this transistor is called Shockley transistor. Shockley. I hope all of you have heard this word, Shockley. So William Shockley. So these are the guy at the middle. He is the main guy, and the other two are the helper, or I should say associates. In 1947, they created this. Okay, let's go back to another person. Julius Edgar Lilienfeld. I hope all of you have heard this name, Lilienfeld. Julius Edgar Lilienfeld was an Austro means Austrian, Austro-Hungarian physicist. That time, before the World War II, maybe the Austria and Hungary was associated. So he is from Austria, Hungary. So he was an Austro-Hungarian physicist. He was born in Lemberg, Austria-Hungary, now called Lviv in Ukraine. Now that place is called Lviv in Ukraine. Moved to the United States in the early 1920s, originally in order to defend patents he possessed, and then made a scientific or industrial career there. He invented a FET-like, FET, field effect transistor. FET-like, not a transistor, but FET-like something like transistor. So he created or invented a FET-like transistor and the electrolytic capacitor in 1920. I said again, he invented means he invented that thing on paper. That means as a paper, not a physical unit, okay? He invented the theory. Okay, this is how a transistor can work, or something called transistor can work like this. He invented something like that. Okay, in 1920s. Then he filed for a patent. You understand patent? Patent means, do you know patent? What is a patent? Ashik, patent ki jano?
Sir?
What is patent?
Yes, sir. Patent bola hoy apnar সত্য যেটাকে বলে বাংলায়।
Exactly. সত্য. Patent. So he actually created a FET-like transistor and an electrolytic capacitor. Then he went to USA to defend the patent. Defend patent means what? He filed for a patent, then he defend the patent. That patent actually accepted after 1 year, not 1 year, 1 decade. That means after 10 years. See, US patent, this for an FET-like transistor was granted January 28, 1930. That means after 10 years it was granted. Okay. Now brief history. A FET-like transistor by Julius Edgar Lilienfeld was created in 1920. In 1930 that was granted. First transistor was created at AT&T Bell Lab 1947 by William Shockley, John Bardeen, and Walter Brattain. That was a germanium transistor based on the FET-like transistor, because this was a paper. They created the transistor based on that paper, So Julius Edgar Lilienfeld is not an what should I say? Unimportant name. It is also important because he created that paper that helped these three guys to create that transistor. Understood? Okay. This was germanium. Then, but remember, this is not a single crystal germanium transistor. This was actually a piece transistor. That means they actually mixed few pieces together and create a transistor. A first single crystal transistor was created in 1950. That was germanium. Then first single crystal silicon was created in 1952. First IC device. IC device means first IC device. First IC was created by Jack Kilby in 1958 by Texas Instruments. TI. Texas Instruments is one of the leading IC manufacturing company still now. So Texas Instruments launched first, not launched, they invented first IC device that was by Jack Kilby. First IC product means for commercial use, was an IC for Fairchild camera, a camera IC. A camera IC was created by Robert Noyes in 1961. Okay, let's see some images. This is the first transistor, the three guys. This is the first IC made by Jack Kilby of Texas Instruments in 1958. So here you can see 4 pins, 1, 2, 3, 4, maybe 5. 1, 2, 3, 4, 5. One of the pins is not there. Something like that. Okay. This is the first IC. Now this is the first commercially available silicon chip, commercially available for Fairchild camera. Here you can see it has 6 pins. 1, 2, 3, 4, 5, 6. 6 pins are there. Okay. And this is a round circle IC, round. So this was for Fairchild camera and it was created in 1961. Okay, not that. Now come here. Okay, this was the first transistor that was very, very huge, right? That was huge. But nowadays, transistor is very small. How small? Can anyone guess? How small is this? Can anyone guess? Can anyone give me some idea about how small a transistor is?
Sir, like what 555 IC. Like what 555 IC.
555 IC, একটা ট্রানজিস্টর 555 IC সমান?
না স্যার, আর ছোট আছে।
আরো ছোট আছে না? কত ছোট আছে?
Nano size, sir.
Nano size. Okay. Okay, nano size. It is in nano size. Actually, it is in nano size. Okay, nanometer size. So, okay, let me give you one hint. You have phone, right?
Yes, sir.
You have phone. Inside your phone, there is a processor, right?
Yes, sir.
Do you know how many transistors a processor has?
Billion, sir.
Billion, right?
Yes.
Billion. 10 billion. Nowadays, what should I say? The latest processor has a billion ICs. Not billion ICs, billion transistors in one IC. One IC, okay? 10 billion transistors is there in what? In iPhone 11 processor. 10 billion transistor in iPhone 11 processor. So you can imagine how many transistors you have. So transistors are actually becoming smaller day by day. And that means they are becoming smaller means you can put a lot of transistor in one IC. You can put more transistor in one IC. So the transistors are becoming smaller. There is a law on that. That is called, not law actually, this is a trend. So Moore's law, this is called Moore's law. Although this is not a scientific law, this is a prediction. In 1965, Gordon Moore, who is Gordon Moore? Gordon Moore is the Intel co-founder and chairman. Okay, Intel co-founder and chairman, Gordon Moore. He predicted in 1965 that transistor would continue to shrink. Transistor would continue to shrink. That means transistor will shrink day by day. It will become smaller, allowing double transistor density. Remember, this is a Viva question. So please give some emphasis on this. Double transistor density every 18 to 24 months. double performance every 18 to 24 months. Okay, let's say 24 months. That means the number of transistor in same space. The density means what? Density means at the same space. Let's say this is your processor size. Number of transistor here will become double after 2 years. That means in 2020, let's say you have 10 billion transistor. In 2022, you will have how many? 20 billion transistor. That means double. So double transistor density every 18 to 24 months. That means since the transistor number is double, so the performance will be double as well. Double performance every 18 to 24 months. So he predicted this thing in 1965, and it is still correct. Not 100% correct, but correct. Want a proof? Okay, let me give you a proof. Before 2 years, you bought a phone, right? That phone is no longer the most powerful phone in the world. You can buy a similar priced phone that has double performance, right? You can buy a similar phone by using the similar money that has double performance. That means double powerful, double speed. Understood?
Yes, sir.
Okay. So, but is this law will continue forever? No, it will not continue forever, because you cannot shrink a thing, what should I say, infinitely. You cannot shrink a thing infinitely. After some moment, you will see, if I shrink this thing anymore, it will not work. After some moment or after some years, you will see, if I shrink the transistor anymore, the transistor will not work. Why? I will explain later. So that is called physical limitation. If I shrink the transistor anymore, the transistor will not work. That is called physical limitation. That means we cannot shrink that anymore. Another limitation is there, economic limitation. Because if you shrink transistor more, you need more investment. Why? Because you need to change the, what should I say, the shrinking machine after 2 years, after 2 years, after 2 years. So more shrink, that means more money you have to put. After some moment, you will see, if I shrink this thing anymore, the cost of shrinking will go up so much that the people will not buy our IC anymore. So that is called economic limitation. So either one will stop the trend. Either the physical limitation or the economic limitation, whichever comes first will end the trend. That is the time when we have to move to another computing system. Perhaps the quantum computing system, perhaps. That time our transistor-based computing system will not work. Okay. Not necessary. Okay, this is ASIC, the mask layout. Remember this word, mask layout. M-A-S-C, mask layout of ASIC. ASIC is application specific integrated circuit. Application specific integrated circuit. Okay, excuse me for 30 seconds. Okay, this is the ASIC. ASIC means application specific integrated circuit. That is with mixture of full custom RAM and a standard cell. That means, what is ASIC actually? ASIC is when you design an IC for a specific purpose, that is called ASIC. Like a television, you are going to make a an IC for a television. The purpose of this IC will be processing the TV channel videos, right? So actually, you know, before manufacturing the IC, you know it will be used in TV. So that's why it is called ASIC, application specific integrated circuit. That means this is only made for TV. You cannot use it for computer. You cannot use it for camera. You cannot use it for let's say a mobile phone. You cannot use. So that's why it is called ASIC. Now, what is not an ASIC? What is not an ASIC? CPU, phone CPU or computer CPU, something like that. Why? Because the phone CPU, you do not know. People will use it inside the phone or inside the TV or inside the Android box or inside the car. You do not know, because you can use it anywhere as a CPU. Normally, it is used in phone, we know it, but you can use it inside a car for the operating system, Android-based operating car, right? There are some cars available already that is Android-based, right? There are some camera as well, that is Android camera. There are some TV, Android TV. There are some, what should I say, computer, like a laptop computer that is Android-based, some tablets Android-based, and some home automation system that is Android-based, right? You can use that processor in anything. So you do not know where it will be used. So that's why that is not ASIC. ASIC is you know where it will be used, and not ASIC. That means there is a name actually. There is a full custom design, full custom CPU or an IC. So you do not know where it will be used. Okay, you can program it later. Here you do not need any programming. The programming is already done inside while making it. So you know it will be plug and play. So you take it and you plug it, so it will be okay. You do not have to do any programming. Okay. Now this is the mask layout of a Pentium computer. Pentium, not Core i3, not Core i4, 5, Core i9. No, not that. This is a Pentium computer mask layout. Here you can see some red colors, some blue colors, some pink colors, purple colors, some green color as well, right? There are some reason behind these colors. These are actually different element of a mask layout. We will be doing some mask layout in our lab as well. In our lab, we will be doing some mask layout, but not this big. We will be doing very small mask layout. Just we'll have an idea how it is made. Okay. So here you can see different parts of a CPU: clock driver, code cache, code TLB, pass interface logic, data cache, data TLB, MP logic. All those things are there. Okay. Now let's see a Core i7 or Core i9 mask layout. Oh, okay, this one. Okay, you can see a very, what should I say, very tiny actually, a very hazardous, or I should say very, what should I say? Okay, you can see a mask layout. This is a Core i9 mask layout. Here you can see how many cores do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 core, maybe 20 core or 10 core, I do not know. I'm not sure. 20 or 10 core Core i9 processor. Okay, this is the mask layout of Core i9. So which one is the mask layout? Which one is the mask? Where it is situated? Why it is there? Where? If you open this metal cap, you will see something like this. Something like this, right? Intel. If you open that cap, this is the cap, right? If you open this cap, here is the triangle. Can you see a triangle? Here there is a triangle. Here. Can you see a triangle? Hello?
Yes, sir, we see.
Okay, this is the triangle. This is the indication. And now you can see there is a triangle, right? Can you see
Yes,
the
sir.
triangle? Okay. So that triangle is this triangle. So when you open the metal cap, you will see a box like this box, right? This is the CPU.
Yes.
This is the CPU. That means this is the mask. This is the layout. This layout is printed or transferred to a silicon wafer. This is the silicon wafer, and the whole base is the pins. All the pins are there. Okay. Here you can see. Here you have a CPU, and here you have a GPU, graphics, integrated graphics. Okay. This is the CPU. This is the graphics, integrated graphics. Understood? So at first, the VLSI engineer will make this design, and the other engineer will transfer that design to a silicon wafer. What is a wafer? This is a wafer. This is a piece of wafer. Okay. Okay. Let's see. What is a wafer? This is a silicon wafer. Can you see a silicon wafer is this? This is a silicon wafer. A person is holding a silicon wafer, a sheet of wafer. There you can see a lot of boxes, right? Some boxes, right? Can you see that? All of them are one CPU. One CPU. See? Those boxes are cut. Those boxes are cut later. Each one is one CPU. Each one is one CPU. Normally, a silicon wafer is like this, like this. Then the design is transferred. This design is transferred to the silicon. Then that is look like this. After that, you are going to cut them in pieces. Okay. After that, you are going to cut them in a pieces. When you cut them in a pieces, you can have CPUs. One CPU. That time, this CPU will be placed. Where? Wait. Will be placed here on a casing. Okay, on a case. After that, that case will be covered with a metal piece. This metal piece will help the heat to go out. Heat. It will help the heat to dissipate. Okay, that's it. Understood, my dear? What is a wafer?
Yes, sir, we understood, sir.
Silicon wafer is this one. Silicon wafers are this one. Okay, these are actually cut from. The piece of silicon. They are cut from piece of silicon. Okay, like this. A piece of silicon is this one. They are then cut slightly. What should I say? Very thinly they are cut. So at first, silicon wafer or silicon tube looks like this. This one. Then they are polished. Then they are cut in a very good manner. Then they are sliced. Understood? Silicons are there like that. Okay. Now, what we are going to do in this course, I'm going to give you some idea. Okay. So I'm going to stop the recording because the recording is no longer required.